Okay, let's just jump right into this explainer. Today we're uncovering the hidden, heavy-duty manufacturing mechanics that literally shape the everyday objects all around us. You know, it's incredibly easy to just go about our day surrounded by cars, bridges, airplanes, and appliances without ever stopping to think about how these massive, totally unyielding metal structures were actually made. Well, today we're going to explore the brutal yet beautifully precise world of metal rolling.
Think about a typical car for a second. It is absolutely fascinating to realize the sheer ubiquity of metalworking here. A single car contains everything from thin, drawn wire for the radio antenna to thick, stamped plates for the wheel covers, right down to the deep-drawn pans holding the oil. Every single one of these metallic components started out as something much simpler, and it had to be manipulated through intense, highly calculated physical forces to reach its final state. It's honestly a symphony of manufacturing, and metal rolling is the lead instrument.
Part 1. Forming and shaping our world. Let's establish some core concepts.
Okay, before we get to the heavy machinery and sparks flying on the factory floor, we need to get our terminology straight. Because in manufacturing, words really matter. We've got two primary ways to manipulate raw materials. First is forming, which involves bending or physically manipulating a solid body that already exists. Think of taking a stiff piece of wire and twisting it into a coat hanger. The material was already solid, you just changed its geometry. Shaping, on the other hand, involves molding or casting something right near its final shape completely from scratch, like injecting molten plastic into a cavity to make a video game controller. For this explainer, we are focusing squarely on forming, specifically the continuous, high-pressure deformation of solid metal.
Moving to Part 2, the science of flat rolling. Let's zoom into the roll gap.
So let's look at the microscopic physics of this gap, where an astonishing 90% of all metals produced by metalworking are squeezed down to reduce their thickness. When a thick piece of metal enters the gap between two massive steel rolls, it actually accelerates, kind of like fluid flowing into a narrow pipe. But how does it get pulled through? Well, it feels totally counterintuitive since we usually try to eliminate friction in machines, but here, friction is absolutely essential. It's the friction that pulls the metal through the rolls without slipping. The maximum reduction in thickness you can get in a single pass, which engineers call the draft, depends entirely on the roll radius and the friction. Think of a farm tractor. To pull a heavy load over rough terrain without skidding, you need massive tires with a large radius and deep treads for high friction. Of course, in metal rolling, too much friction will completely destroy the surface finish, so operators have to strike a really careful balance using specialized lubricants.
Now, because the rigid rolls are spinning at a constant speed, but the metal is stretching and accelerating as it's squeezed, there is a whole lot of relative sliding happening. But right in the middle of that contact zone is this magical spot called the neutral point, or the no-slip point. This is the exact location where the velocity of the metal perfectly matches the surface speed of the rolls. By calculating what's known as forward slip at the exit point, operators can pinpoint exactly where this neutral point is. And this isn't just fun trivia. Knowing this actually allows engineers to monitor the surface finish of the metal in real time and control the immense, multi-ton forces at play inside the mill.
Part 3 brings us to hot and cold rolling, a tale of two temperatures.
Temperature is basically the ultimate cheat code in metalworking. We generally divide the process into two main phases. The initial breakdown of the material is done through hot rolling. This happens at blistering temperatures. We're talking up to 1250 degrees Celsius for steel and 1650 degrees for refractory alloys. This is above the metal's recrystallization temperature, making it nice and pliable. Cold rolling, conversely, happens later on at room temperature. So while hot rolling does the heavy lifting of breaking down the raw ingot, cold rolling comes in to refine the metal, giving it a beautifully smooth surface finish, tighter tolerances, and much higher strength due to strain hardening.
But why do we have to hot roll first? Well, when metal is first cast into an ingot, its internal structure is coarse, porous, and really brittle. It's just weak. Hot rolling subjects this brittle cast structure to immense compression, physically crushing and breaking up those brittle grain boundaries and closing up any internal porosity. It literally heals the metal from the inside out. This transforms it into what we call a wrought structure, which has fine, uniform grains and the ductility it actually needs to survive in the real world. To put this into perspective, the scale of thickness that rolling can achieve is absolutely staggering. When the metal is thicker than 6 millimeters, we call it a plate. These can be up to 300 millimeters thick for massive bridge supports, or 150 millimeters for the walls of a nuclear reactor vessel. As we keep rolling it thinner, below 6 millimeters, it becomes a sheet, like the 1.8 millimeter skin keeping you safe inside a Boeing 747. And if we just keep going, applying more passes and more pressure, we reach foil,
dropping all the way down to a paper-thin 0.008 millimeters for the aluminum packaging sitting in your kitchen right now.
And to keep up with global manufacturing demands, we need a lot of this stuff. So these continuous sheets of rolled metal aren't usually shipped as flat squares. They are spooled up and supplied to factories as massive, continuous coils. A single coil of sheet metal rolling off the production line can weigh an astonishing 30,000 kilograms. That is over 66,000 pounds of perfectly uniform sheet metal, just waiting to be stamped into refrigerators, cars, and soup cans.
Part 4. Massive mills and equipment. Let's look at the titans of industry. You really have to zoom out to comprehend the sheer scale of a modern rolling mill. These are multi-million-dollar, highly automated facilities that can stretch the length of several football fields. And they don't just gently press the metal. The strips can rocket through this equipment at blistering speeds of up to 40 meters per second. The power required to do that is immense, and managing these forces requires some truly incredible engineering. Here is a wild thought. The separation forces are so incredibly high that solid steel rolls actually bend elastically, just like a rubber tire flattening under weight. If the rolls bend, the sheet comes out thicker in the middle, which is a defect called a crown, or it gets wavy, buckled edges. To stop this, engineers came up with brilliant multi-roll configurations. A basic 2-high mill is fine for initial rough passes, but a 4-high mill uses 2 smaller work rolls backed up by massive, super stiff backup rolls to stop deflection. And for super thin foils, they shift to cluster mills, where a tiny work roll is completely surrounded by an entire constellation of support rolls. Finally, Part 5, specialized rolling processes, because it goes way beyond just the flat sheet.
Rolling can actually manipulate metal into complex shapes without ever cutting it or generating scrap. One of my favorite examples of this is the Mannesmann process, which makes thick-walled, seamless pipes. It relies on a bizarre quirk of physics. If you apply radial compressive forces to a solid round bar, basically squishing it from the outside in a cyclic motion, tensile stresses will actually tear a small cavity wide open right in the center of the solid core. Seriously, you can test this. Take a round pencil eraser and roll it back and forth heavily on your desk. Eventually, the center will just give out and hollow itself. By combining this trick with skewed rolls that pull the hot metal over an internal mandrel, we continuously manufacture heavy-duty, completely seamless pipes for high-pressure oil and gas.
Another mind-blowing application is thread rolling. If you need a bolt to hold an airplane engine together, you definitely do not want to use a machine tool to cut the threads. Cutting physically severs the grain lines inside the steel, which inherently weakens it. Instead, we use thread rolling. Flat or cylindrical dies literally cold work and mash the metal into the shape of a screw thread. This maintains the internal grain flow and traps compressive stresses inside the surface, drastically improving the fatigue life of the fastener. It makes it exponentially stronger than a cut thread, and it does it at production rates of up to 80 pieces per second with zero scrap. No way, right? It's truly fascinating to step back and consider just how deeply dependent our modern lives are on these invisible, brutal, yet beautifully precise industrial forces. From the structural I-beams in the ceiling above you, to the seamless pipes delivering your water, down to the microscopic foil wrapping your food, the mechanics of metal rolling are literally everywhere. So I'll leave you with this question. How many rolled metal objects are you relying on right this second? The number is probably a lot higher than you think. Thanks for joining me on this explainer, and keep your eyes open for the manufacturing marvels hiding in plain sight.